Every engineer I know has the same complaint. They spend hours every week reviewing code, and half of that time spent on things that shouldn't even require a human. Missing tests, style violations, functions that are 200 lines long but could be 20. Obvious things that sharp eye catches right away, but shouldn't require a human. I was thinking, does that actually have to be human time? So in this video, I'm going to walk you through an AI agent architecture that I've designed that's going to do things better. It sits on every GitHub pull request, does the mechanical work automatically, and gets out of the way before even human gets there. Let's get it started. Here's what the current flow looks like. An engineer opens the PR. A reviewer gets pinged. They're in the middle of something else, they have a meeting, they find the time, they context switch, they skim the diff, they leave some comments, they go back to what they were doing, maybe they'll come back tomorrow. The bottleneck is not the skill. Senior engineers are perfectly capable of reviewing all the code, but the problem is there's much more PRs that needs reviewing than there is actually human bandwidth, right? And the reviews that suffer are from junior engineers who need feedback most. What we're actually making better with an agent is that we're reducing the mechanical work, not by replacing reviewers, but helping them to preload those manual decisions that they otherwise would be doing themselves. So they can focus on the decisions that actually are important and where their judgment is needed, where their experience is valued the most. So the suffer of the context switch is reduced as well. Everybody wins. So what does this look like in practice? An engineer opens a pull request. Within 30 seconds before any human has looked at it, they see comments already waiting, like you can see here on the screen share. Things like function has no error handling, or we're adding some secret keys, or the token expiry time is wrong, or the change isn't covered by test, anything. Then the agent never approves or rejects the PR. The decision always stays with a human. It just surfaces the good things the reviewer would catch anyway, earlier, so the conversation between engineer and reviewer can happen more productively and skip the mechanical things. The two systems that connect to it are Git, well, to read the code changes, obviously, and CI/CD, to see whether the tasks have passed. That's it on the surface. Under the hood, well, it's a bit more interesting. Okay, let's open the hood. The flow starts on the left. GitHub sends a webhook the moment PR is opened. That's just an automatic notification that the PR has been created. And it hits the event receiver. Think of it as a front door of the application. This is the only thing that's exposed to public network. Everything else is private. And the event receiver doesn't process anything itself. It just puts the job into the queue. The queue here is quite critical. It means if 200 engineers open PR at the same time, the system absorbs the spike instead of falling over. From the queue, the orchestrator picks up the job. This is the brain of an agent. It runs what's called a react loop, reason and act. It asks the LLM what it needs. The LLM requests information. The orchestrator fetches it, and they go back and forth until LLM has enough to write the full review. Think of it like a project manager coordinating between specialists. The tools are right here. So Git, CI/CD, knowledge database, any style guides, your Jira tickets in the ticketing requesting system. It cannot push anything. It's only read-only. We have to ensure that this system is safe. So this can only read the data. It doesn't write anything. The LLM goes through the gateway. So this handles rate limiting, cost tracking, failover between providers. In case we use a few models or Anthropic has an outage, we reroute to OpenAI. The agent does not care which model answers in some cases, right? So finally, the output writer, once we have enough information, it posts the review to the PR as inline comments. This is the only component that's allowed to write back to GitHub, and only as comments, not approvals, not mergers, not anything else, just comments. So that constraint is enforced on infrastructure level, not in the application code. Two things are worth noticing are at the bottom. So the tool registry and the auth policy engine. These exist because this isn't designed as a single agent. It's designed as a platform, and any team in the org can build their own agent, plug this into the infrastructure, and they get all of this, the security model, the observability, the cost tracking for free. They just write a system prompt and, well, pick their tools. That covers the general overview. Further section, we're going to cover the deep dive for engineers, where we're going to look more in depth of how these services work and coordinate between each other. Let's go one level deeper and talk about what's actually running inside of each of these boxes. So starting from the event receiver, it's a FastAPI application running behind an Nginx controller on Kubernetes. The moment GitHub sends a webhook, the first thing it does, it verifies the hash of the pull request using the standard library. If the request fails, then it's rejected before it touches anything else. Valid events are serialized with Pydantic and dropped onto the queue here. That's using SQS. The pod itself is quite tiny. It's a fraction of the CPU, 256 megabytes of RAM. It does almost nothing except validate and enqueue. Two replicas are always running for availability. The queue is AWS SQS. Managed infrastructure, nothing custom. SQS handles the scale quite comfortably without operational overhead. So alternatives would be Kafka if you need something more complicated, but Q is essentially decoupling the event receiver from the orchestrator that we see here. So if 200 PRs are published all of a sudden at once, then they sit in the queue and the workers process them at their own pace rather than everything crashing at once. The orchestrator is where our custom Python code lives. It's basically an async worker. It consumes the jobs in the queue, right? It runs the React loop, reason and act. It's currently here we're not using LangGraph. It's using the MCP to talk to the tools, which is a model context protocol developed by Anthropic for standardizing how LLMs connect to tools. But basically, LangGraph here is too bulky, so we're gonna run something more simple. But whenever a project becomes bigger, it's very easy to integrate LangGraph here. Structured output is enforced with Pydantic again, so the LLM is prompted to return JSON. And if it fails the schema validation, then the worker retries once before logging the failure and exiting. Workers here, they scale horizontally with Kubernetes, which watches the SQS queue depth and spins pods up depending on requests. So it could be 5 workers, it could be 20. You pay for what you use. The tools here are their own small fast API service. It's a separate Docker image, separate deployment, separate dependencies. For example, the Git tool just uses the PyGitHub to fetch diffs, file history, and PR metadata. It authenticates to GitHub, uses the private key stored in AWS Secrets Manager, and it's fetched at the startup time. The private key that we need for the GitHub access. So the other things are fairly similar. The ticketing and CI/CD tool, it's all the async workers to retrieve the data. Now the LLM gateway. So it's done as an LiteLLM. It's an open source proxy that gives every service a single OpenAI compatible endpoint, regardless of what model is actually behind it. So it's better for provider abstraction. So if you want to add a fallback model, swap providers, or test a new model release, you just update the config file and you don't touch the application code. LiteLLM is very good at retry logic, fallback routing, and it logs token counts and latency on every request. And token counts is something that's going to be very important on your usage bill. So on top of it, we run a thin API layer that adds rate limiting. So it's using Redis to make sure that we don't queue the service too much. So on the question of output writer, actually, it's another relatively simple PyGitHub service. So it's the only one provisioned with write access, right? Everything so far here was read focused, but basically here, once we have everything ready in the JSON, it has the only GitHub permission. Pull requests, write. It literally cannot approve, merge, or push. And before posting anything, it catches any maybe credentials that could have been echoed back. It validates the full Pydantic schema one more time. Then it posts each comment to the exact file line number, just like I've shown you on the PR in the previous section. So the constraint is it only posts the comments, right? It's not a setting that you can toggle. It's just what credentials allow, okay? So every Docker image in the system follows the same pattern that we're gonna deploy. It's going to be a slim Python 3.12, right, as the base. And what else do we need? We need a non-root user, right? We need to define how big is our images. So they can stay small, between 180 megabytes and 350, depending on the service. Each one literally carries the libraries that it needs. So at the bottom is actually a very interesting thing that we should not forget about is observability. So it runs on OpenTelemetry. So every FastAPI service is auto-instrumented with the OpenTelemetry instrumentation FastAPI. It traces, takes the traces and ships it to the Datadog or Grafana so that you can basically track it and make any dashboards that you might need in the future. What other things we might need is the cost dashboard. It's also done in this bit, and there's 3 metric layers. Basically, infrastructure metrics are scraped by Prometheus from Kubernetes. The application metrics are exposed on each service metrics endpoints using also Prometheus clients, and AI-specific metrics, token usage, cost per review, comment acceptance rates. It's all written to Postgres table, tagged by the agent, repo, model, and timestamp. So the last one is your cost dashboard and, well, your trust signal in one place. And that covers most of it. I'm gonna put all the tools that we have used on the screen on the left so that you can research them and put it once again all together. If you feel there's a need to map it out in your head once again, please rewatch this section. All right, so 3 decisions that I want to highlight because they are where most of these systems go wrong. First, credentials. The easiest version of this is to put API keys in a Docker file or environment variable. That's also how you end up with leaked credentials or them being baked into your container and can be visible with everyone who can pull them. The better answer is IAM roles. So the pod has an identity. The identity has permissions and, well, no secrets are ever passed. Nothing to leak, nothing to rotate manually. Second is chunking. A large PR might have 2,000 lines changed across 15 files. That does not fit in a single context window. The naive approach would be to just cut it in half. The right approach is to prioritize. Anything that touches authentication, payments, data models gets a deep review first. Boilerplate config gets a summary pass. If we genuinely cannot cover everything, the agent says so explicitly instead of pretending that it has reviewed files that it didn't. And third one is evaluating a non-deterministic system. How do you even know the agent got worse or better after you change something? You can't use the exact match. There's no simple way to write tests, and the same good review for the PR can be written a dozen different ways. So we maintain a golden data set of historical PRs with known good reviews and the most important high-level bugs that it should catch in important files, and we run this test on every version change. We score outputs based on semantic similarity. Not perfect, I agree, but it's the most honest proxy that we can have. In the next session, we are going to cover how we measure success. Here's 3 metrics I tracked from day 1. First is comment acceptance rate. So once the agent leaves the comments, do engineers actually act on them? Because if that number is less than 50%, means the agent is just, well, adding noise, not adding value. Second is PR turnaround time, something to be measured before agent is rolled out, and obviously should improve once the agent is connected to the GitHub. Third one is voluntary adoption. Do people actually get interested about the agent? Do they sign up for it? Do they use it? And do they not opt out? One of the things that are very important in the first few months is the opt-out rate. If it's quite high, it's something that we must fix early on. It's easier to notice and much harder to deal with as we go on further. The thing that I found the most interesting is not the AI part, it's the platform part. Building one agent is the project. Building an infrastructure that allows 50 other teams to build their own agents on top of it, that's the product. The design decisions that matter the most are actually the ones that make the second agent easier than the first one.